present some of their research results over the course of this presentation. So I'll start out with just a little bit of information about the Power Electronics group here at UTK. In addition to myself, we have 3 other power electronics focused faculty, Dr. Fred Wong, Leon Tolbert, and Kevin Bai. A relatively large program of over 40 students, graduate students focusing on power electronics. We are the host site of the NSF and DOE Engineering Research Center Current, which focuses on transmission network and collaboration between power electronics and power systems. Many of us, since we're so close in proximity, have joint appointments, myself included, with Oak Ridge National Lab, where we work on some additional wireless power topics mostly related to electric vehicles. And then we are the host of a wide bandgap traineeship sponsored by the Department of Energy that we've named Potential, with these 2 N's for Tennessee. And that website will be a good resource for information on a lot of the research going on here in the center. So within power electronics at UTK, we focus on a wide variety of applications, and I'm going to talk just briefly about some of the other research that we do before I delve in some detail into the main topic for today, which is wireless power transfer in the consumer electronics space. So within utility applications, one example previous project, we designed a transmission scale reactor at 115 kV and 1.5 kiloamps and used power electronics to inject a DC current that would gradually saturate the core and result in a controllable impedance. In medical devices, kind of on the other end of the spectrum, we've gone as low as 100 millivolts and 100 nanoamps for the design of implantable RF energy harvesting. It uses far-field RF wireless power transfer to power fully implantable devices. And then worked on things like electrosurgical generators, use intelligent control of wide bandgap inverters to generate multiple frequencies for improved surgical outcomes. In electric vehicles and aerospace, we work particularly closely with Oak Ridge National Lab on electric vehicle applications. So here on the left, it's showing some work we've done that focused on functional integration of different power converters within an electric vehicle to improve efficiency and size, weight, and cost. And then perhaps a less traditional electric vehicle, we're looking at future generation aircraft, working together with Boeing and sponsored by NASA. We're currently working on the design of a 1 megawatt motor drive for a cryogenic application where all the power electronics are cooled by minus 200 degrees C coolant. In kind of the power supplies area, we've done a few different projects where we've designed complete power conversion systems for data centers, looking at different AC inputs and going all the way down to 1.2 volts, focusing on improving efficiency through intelligent design of these different converters and also reducing the number of cascaded conversion stages. These deploy both silicon and wide bandgap devices, silicon carbide and gallium nitride in their implementation. Renewable energy, we were a finalist within the Google Little Box Challenge, which wasn't explicitly a solar inverter, but we're continuing the developments there to design future solar inverters focusing on lifetime cost improvements. And then within the smart home and microgrid type space, the one project that I'll highlight here is our hardware universal grid emulator, or hardware testbed, which is a complete room that we've built up with variably controlled DC to AC 3-phase inverters that we can control to emulate different components in order to generate kind of our own isolated power system that we can use to run studies on different small segments of a power grid or a microgrid. And then in the core technology space, we worked on things like gate drives for wide bandgap and power module design around wide bandgap transistors. And then looking at applications of different technologies, here just talking about 3D printing for mechanical and thermal, as well as magnetics design within power electronics. And then finally, in consumer applications, a couple of projects as an example here, worked on-chip power conversion for high efficiency and high current battery chargers for things like cell phones and tablets. And then the one that I'll really focus on today is our wireless power transfer work for consumer electronics that I'll delve into with the remainder of the presentation. So if any of these topics interest you outside of the focus of today, there's more details available on the website here. I'd invite you to look at those or email me at any point. But what I want to focus on today is this project, which we're working together with PowerAmerica on, which is the design of a multi-load wireless power supply. The intention here is shown by this kind of mock-up on the left, that we would have a system where any sort of consumer electronics, any sort of mobile devices that you place on top of a tabletop within a moderately constrained area immediately are picked up and begin wireless charging without having to plug anything in and without having to put them in any sort of designated charging location. So the general specs of it are listed here. We're looking at 100 watts and 6.78 megahertz, greater than 90% efficiency and high power density, and then being able to service multiple loads, which are somewhat free spatially. So with the remainder of the presentation, I'm going to kind of begin by talking about just some fundamental analysis in case anyone in the audience is unfamiliar with this area, and then use that to motivate some of the design decisions and directions forward in designing these wireless power systems. And then I'll talk about what current systems, current wireless power transfer setups look like, and then show some of our research results on avenues for improving them. So just to start with the basics of wireless power transfer, what I'll focus on today is inductive power transfer, as opposed to things like capacitive power transfer or far-field RF, just due to the maturity of the technology and the suitability for the application that we're looking at. So the basic idea of this is that I'm going to have a coil of some conductor, effectively forming a spiral inductor here, and I'm going to use a source to put some AC current at a given frequency through that coil. In doing so, I'll generate some flux that flows through that coil in kind of closed loops that I'm just truncating here. And then if I create some separation, so this black material would be some non-magnetic, non-electric material that separates this coil from anything above it. I can then place a second coil, and if any of the flux generated by that first coil penetrates through the spiral of the second coil, it will induce an AC voltage, here shown as VRX. If I then connect some load to that, I can begin transferring power from the first coil to the second coil without any direct electrical connection between the two. More interesting, perhaps, for the application that I outlined would be looking at if I have multiple smaller receiver coils, all positioned here, all unconnected to the transmitter. As long as some of that flux penetrates each of these coils, they'll all generate voltage. And here in this diagram, I'm showing kind of a couple of different positions where the coil on the left would have a fair amount of flux penetrating it and therefore generate a relatively high voltage, whereas the one on the right might generate a lower voltage because it has less coupling to this flux. That's the basic idea. And this sort of technology, this inductive power transfer, has been developed and is commercialized. You've probably seen out there things like these Samsung chargers shown in the top right. What's out there now is largely one-to-one, largely requires both of these coils on the transmitter and the receiver be well aligned, and it requires that whatever you're charging, the cell phone or watch in this case, be placed specifically in a certain spot so that the system can operate as expected. What we're trying to work towards is something that doesn't have these spatial constraints, doesn't require directly placing the phone on this stand, but as long as it's somewhere in the vicinity of the transmitter, it can pick up and start charging. In addition to the spatial freedom, we'd like to, of course, design for kind of traditional power electronics goals like high efficiency, low EMI, and high power density. High power density is going to be particularly important for integration into things like cell phones, where there's an expectation that the charging will work as well as wired charging, be just as fast, and very limited space available on a cell phone to implement additional circuitry. When we get into analyzing this type of configuration, these two coils from the transmitter and receiver are going to look like a pair of coupled inductors with some coupling factor K. If I look at kind of the top left, the first setup I showed where I have matched coils, most of the flux from the first one penetrating the second coil, I'll get a coupling factor in the 0.5 to 0.7 range. If I start looking at smaller receivers, I could be as low as 0.1 or even below that. but we'll be able to model kind of the basic behavior of either of these as a pair of coupled inductors shown here in this circuit diagram, LP and LS, where the subscript P will refer to anything on the primary on the transmitter side, and the subscript S will refer to anything on the secondary on the receiver side. In addition to those coils themselves, I'll have resistances RP and RS, which are the parasitic resistance of each of these coils, which is unavoidable, but parasitic and should be minimized. And then I've also added here some impedance ZP and ZS, which just represent any additional impedance in this loop, which I either insert intentionally or results from parasitics. And I'm going to go through some basic analysis of this circuit that's kind of widely present in the literature on this area. I'm going to make an assumption here that all of the waveforms, regardless of the wave shape of VTX, are dominantly single frequency through these coils. And that's not immediately justified, but is going to somewhat need to be enforced by design. If I have a wide variety of frequencies going through this, I'll have higher AC losses and potential EMI issues. So looking at the analysis of this circuit, I can divide it up here, just replacing the two coupled inductors with voltage sources corresponding to their mutual inductance, and write KVLs in this blue loop on the primary, or the blue equation, and then on the secondary in red. I have equations written below for the KVLs around those loops. So looking, focusing on kind of the secondary side here in this red loop, what I see is that for a given load resistance, the power going to the load is going to be dictated entirely by the current flowing through this loop, and that current is all induced by this j omega m IP source. So I can say that for a given amount of power going to the load resistance, that current comes from j omega m and depends only on the magnitude of the primary current. So one thing I might be interested in looking at is the ratio of that primary current to the secondary current, and I've written an expression for that down here at the bottom. Without going through kind of a full derivation for why we do this, just inferring from that relationship here, see that for a given output power, my secondary current is constrained, and then based on this ratio IP to IS, any additional reactive impedance from this LS inductor and then this additional source that I put in series is only going to increase my primary current and then increase any losses I have in the primary resistance. So having any additional reactive impedance here is only going to degrade my efficiency. On the primary, I have kind of the same setup with this reactive impedance XP and LP. That will have largely no effect on the efficiency, but will only distort what I need out of VTX. So for efficiency reasons, I'm going to try to cancel out any impedance seen on the secondary, this j omega LS plus JXS, and I'll do that by implementing JXS with a series capacitor that resonates with LS at the frequency omega. And on the primary, just for simplicity, I'm also going to cancel those impedances so that I can reduce this down and get rid of the reactive elements of the circuit. But I'll note that for control reasons and potential operation under unloaded and boundary conditions, this may not be the best thing, but since it has no effect on efficiency, and that's one of my primary concerns in this analysis, I'll just go ahead and do that. So by canceling that reactive impedance, what I end up with is a circuit that looks like this. Now I've greatly simplified everything. My ratio of primary current to secondary current now looks just like the sum of the impedances on the resistances on the secondary divided by this j omega m term. And now I can look at and solve for an expression for the efficiency of power transfer from VTX to the load resistance RL. And that's going to look like this expression at the bottom, which is just the output power averaged over one period divided by that output power plus all of the losses, which in this case are just the power consumed by RP and RS. Since these two linked sources represent the magnetic mutual inductance, there should be no loss on that. And then I can simplify this expression by dividing everything through by the numerator. And what I get is in the middle here, some expression that depends on the resistances, and then this ratio of IP and IS, the magnitude of them squared. And fortunately, I've already solved for the ratio of IP to IS, so if I plug that in, what I get is the final expression in the bottom right. which has kind of a recognizable form where the term in parentheses just relates to the resistor divider at the output, and then this term in the denominator relates to reflecting things back through these j omega m sources, like pick up a square on my omega m. So this is the efficiency of this circuit. One thing that I might want to look at is, okay, what is the load resistance RL, which will give me the greatest efficiency? In order to do so, without kind of going through the full analysis here, every step in this derivation, I'm going to take a partial of that efficiency expression with respect to the load resistance, set it equal to 0, and solve that my optimal load resistance has a form that looks like this, RS times the square root of this term. And then plugging that back into my efficiency expression, what I get is what's shown on the bottom here, or replacing omega m squared by the Q of the two inductors and the coupling factor between them. I can get that into a form that's kind of more present in literature, which is this K squared QP QS term divided by 1 plus the root of 1 plus that term. And this is the one that you'll see in a lot of papers talking about wireless power transfer. So from that analysis, I can conclude a few things. First, that my efficiency, my maximum achievable efficiency, is going to be this expression, which depends largely on my K and then the Q of my two inductors. And if I want that efficiency to be very large, then I want this product, K squared QP QS, to be as large as possible. Going to lead towards me wanting to design this system with really high coupling between my transmitter and receiver and low loss coils so that their Q is quite high. Just as an example here, if I want to shoot for 98% efficiency, then I need to design this K squared QPQS term to be 10,000. And then a note on this analysis, as I mentioned earlier, this is valid really only if we have this ideal cancellation of reactive impedance that I mentioned on the secondary, and only if the load is controlled directly to this optimal resistive load, which can be difficult to do in a real system as I have varying coupling factor and potentially varying parasitic reactances reflected onto this coil from any metal nearby. But there are different ways to do that that I can talk more about as we get into implementation details. And then finally, the efficiency that I'm talking about here is really the efficiency just of this inductive link. So whatever that maximum is has to be high enough such that I can then actually implement this and still maintain a reasonable efficiency of the system. So eta max RL really is before I even start thinking about how I implement the power electronics and what their efficiency is. But just looking at the coils here, I can say, okay, if I want to maximize this K squared QQ term, what I want to do is have really high K and really high Q, so I'm going to look at how I could do each of those in the next couple slides. So if I want to increase the quality factor of the coils, I need to look at how I'm going to operate this system. And here I'm showing an example case with some simplified highly approximate calculations for what I can possibly get out of just a circular coil made out of a solid core wire. So in this example case, I'm looking at a 1/2 meter diameter coil with a varying number of turns made out of 16 gauge solid copper wire. And I'm considering skin depth, skin effect type losses, and radiation type losses, but not explicitly considering proximity losses, so I don't have to constrain the physical geometry, how these windings are spaced. So if I look at a varying number of turns and operation at a varying frequency, what I get is this plot in the top right here of coil quality factor versus the frequency of current flowing through them. It's got 3 distinct regions. Kind of at the low frequency range, my conductor is small relative to the skin depth, so my resistance of the coil just looks like the DC resistance. As I go up above this first dashed line, the skin effect starts to become dominant, and my resistance is going to increase as the square root of the frequency. And then up above this kind of curved dashed line in the top right of the plot, my total coil length starts to approach the wavelength at this frequency. And then radiation effects begin to become significant, which increase the resistance and also potentially represent compliance and safety hazards. So I really want to focus on operation kind of below that boundary. So the quality factor is going to be increasing up until I hit that radiation limit. It increases quickly at low frequency when my DC resistance is constant because the quality factor goes up, omega L goes up proportional to frequency. Then in this middle range, it's going to increase more slowly because the omega L is increasing proportional to frequency, but the R is increasing proportional to the square root of frequency. And then eventually, when the resistance takes off as I approach the radiation limit. Okay. So this is kind of showing that within some limited range up to about 10 megahertz, it's going to benefit me to start operating at higher and higher frequency because the reactive component of the impedance is going to increase faster than the resistive component. This is all for solid core wire. I could also look at Litz wire. And this, based on the reference down here at the bottom, I have a very simplified model of what the additional resistance from the Litz wire would be. See that this allows me to maintain a resistance close to what I had at DC for a longer time, but as I get up into the megahertz range, as is kind of qualitatively shown in a lot of studies, above a megahertz, Litz wire starts to become worse than regular wire due to internal strand and bundle level effects in that Litz wire. Here I'm using 40 gauge. That will give me some increase in Q up to about a megahertz, but then it starts to drop off. So from the combination of those two, it looks like I've got some peak in the kind of high 100 kilohertz range if I use Litz, or I go to solid core and can push up into the megahertz range to get the highest Q. Increasing the coupling factor can be done in a number of ways that largely look at the physical implementation. Common ways today in products are things like either using a lot of different transmitter coils down here at the bottom from a patent put out by Apple, and then powering only the ones which are well aligned to whatever receiver is placed above this coil array. Or, as in the Samsung case and another one, transmitter here from WireX, using multiple coils and then just spatially constraining that the phone needs to go above these coils, and if you charge a watch, it goes above this coil, trying to get good alignment so I can have good coupling factor to each of the receivers. These two approaches, kind of increasing Q and increasing K, lead themselves to discussion of kind of the different approaches to inductive wireless power transfer. So here, just a chart taken from Infineon. Looks at either inductive or magnetic resonance wireless power transfer. These terms are somewhat well understood in the field, though I think they're kind of misnomers in that both categories are both inductive and resonant. But inductive here refers to kind of lower frequency, trying to obtain very high coupling factor, using standards that allow you to operate in the low hundreds of kilohertz. And then magnetic resonance would be looking up at higher frequencies in the megahertz range, focus on high Q, but dealing with low coupling factor, which in turn allows you to have more spatial freedom by tolerating that lower coupling factor. So when we look at frequency selection, in particular related to the target application that I motivated, which is this multi-receiver wireless power transfer, we're going to be constrained to low coupling factor. If I want to have multiple receivers all above this transmitter, each is going to be very loosely coupled to that larger transmitter. So we're going to have a drop in K relative to a tightly coupled case of about 3x roughly. But comparing kind of 200 kilohertz to 6.78 megahertz, what I can achieve in terms of coil Q from these very simplified models, I may be able to get up to a 3x increase in Q because this y-axis is on a log scale, and maybe get just as good a performance out of a multi-receiver application as what I can get out of the commercially common lower frequency and tight coupling applications. And there's some additional benefits if I dig further into this model. If I look at what the behavior of the system is as I change frequency around and change things like coupling factor. So here I have curves of different coupling factor for both the Litz wire and solid wire applications. I'm looking at a single coil of N is equal to 3 and an output power of 100 watts. If I look at where this optimal load is, I see that as I go up in frequency, this optimal load becomes larger and larger. And that can lead to some benefits in terms of the power electronics design and that higher optimal load will allow for a given output power me to operate with higher voltage and lower current on the transmitter side, which may be more suitable to implementation of high efficiency power electronics. Particularly if I'm switching up in the megahertz range, I'd prefer to operate with a transmitter current of 1 amp rather than 10 amps, certainly. And then finally, the thing that we want to think about on the front end in terms of frequency selection is how this is going to relate to things like compliance and safety issues. So here I'm showing just some compliance standards, FCC and CISPR, which will be constraints on far field measurements of EMI at either 30 meters or 300 meters away. And then these ICNIRP standards are safety standards, which will be constraints anywhere that's user accessible. So from the compliance standards, they become more stringent as I go up in higher frequency. I may get some benefit to combat that, and that, as I was showing previously, the currents are going to drop, which might help me meet those. But they have these open bands at the ISM bands at 6.78 and 13.56 are the two lowest ISM bands. And within those, we can go well above these curves. And it may not be readily apparent from the plot, but there's actually gaps in those curves at the ISM bands. The safety standards will not have any gap at the ISM band that needs to be complied with everywhere. But those are on a much larger scale here. I'll just note that CISPR is dB microamps, whereas the ICNIRP standard is amps per meter. So we do need to comply with those. Also note that while ICNIRP is given in amps per meter, volts per meter, and also Tesla, above 100 kilohertz, we really need to consider the RF effects. Those may not be sufficient. But operating up at high frequency allow me to use lower current and get lower field generally for the same sort of application. So it may give me some additional benefit on compliance and safety. There's one more thing I want to address before I start looking at the actual implementation of these systems that I'm commonly asked about is cross-coupling. So cross-coupling occurs when I take this multi-receiver application and actually start putting a load on one of these receiver coils. In doing so, as I load it, there will be current flowing through this receiver on the right, which will cause it to generate its own flux field, which can potentially leak over and couple into the receiver on the left and cause some spurious induced voltage on adjacent receivers. In the sort of application that we're talking about, I'm going to claim that this is largely a non-concern, in that above this receiver coil, I'm going to need to put things like a magnetic shield that will absorb any flux, and potentially also a conductive shield that are going to be necessary in order to prevent any interference with anything above this coil. Putting that magnetic and conductive shield will redirect flux lines down and constrain them from flowing up above this device. And those are going to be necessary if I want to integrate this receiver onto something like a cell phone, where any sort of field that penetrates up above the receiver coil would go into the electronics and cause issues there. So with that, there's relatively little fringing flux that can cause coupling to adjacent receivers as long as they are coplanar and well shielded, which is required by the electronic load. When I start looking at multiple receivers, I actually get some benefit here if I go through and follow the derivation from previously and look at the maximum theoretical efficiency. As I put multiple receivers, assuming they're all completely identical, I get an expression that now has this NR term, which is the number of identical receivers that will increase my KQ product and give me a higher efficiency. If the receivers are all non-identical, I'll point you to the reference down here at the bottom, which talks about that case. Essentially, I get a sum of all the KQ products throughout. This does then shift so that I need to operate all of the receivers in a coordinated way in order to achieve the optimal load and get the maximum possible efficiency. It gives me an opportunity in a lightly coupled case to achieve high efficiency when I have multiple receivers. So with that, I want to kind of reflect back to what we're trying to achieve on this project, working together with PowerAmerica. So here's our mock-up system with a coil, a transmitter coil that we've designed underneath all of these electronics, and we're trying to power various different devices, a laptop at something like 60 watts, a monitor at 25, essentially a cell phone, and then some low power loads, things like a wireless board and mouse that'll be sub-watt type range. And this will sum up to a design that we're going to implement that'll be about 100 watts at a frequency of 6.78 megahertz in that first ISM band. And we're targeting 90% efficiency all the way from the 120 volt 60 hertz AC to the DC output that connects to the actual laptop or cell phone. When we look at the implementation of this complete system, I'm going to start by looking at a baseline system topology that might look something like this, which I'll go through stage by stage here, that goes all the way from AC to the battery on the receiver device. So this system is comprised of a number of different conversion stages. First, at 100 watts, we need a power factor correction rectifier. In most implementations, this is kind of not a focus of the wireless, so it's just using a commercial type power adapter with PFC, commonly a boost type PFC, and then a step down DC to DC converter so that the output voltage can be at low voltage. And just doing some commercial survey, these things are on the order of 90% efficient, pushing up from the 80+ standards. After that, we'll have the transmitter itself, which takes in that lower DC voltage and generates 6.78 megahertz current to flow through the primary coil. Commonly, these are things like Class E or Phi 2 resonant inverters that can switch at 6.78 megahertz while minimizing loss. And if one of those topologies is used, often it's going to require a DC to DC converter out front, which is coupled to the inverter itself that does the regulation of power. Duty cycle control results in kind of bad distortion of these nice resonant waveforms and a significant loss in efficiency as soft switching characteristics are lost. When we look at the coils, here are just a couple examples of different coils. In the low frequency range, commonly Litz wire and a ferrite backing. Here showing one from Worth. In the high frequency range, planar PCB traces are more common with some shielding material behind them. Q can be quite low, particularly in the low frequency cases because of the height requirements, spatial requirements required to integrate it onto a phone or any sort of mobile electronic device. Space is at a premium, so we have to sacrifice on things like thickness of ferrite, sacrifice on thickness of coil. On the receiver stage, power electronics as well as the coil are heavily spatially constrained. So here just showing some example from a commercial vendor of an integrated wireless receiver in a cell phone. Because of the harmonics generated by a silicon diode rectifier, they're required to implement an EMI filter in between the diode rectifier and the coil, and using only low-profile surface mount components that results in significant loss, which then requires the addition of a heat spreader, which has limited effect when in a completely enclosed system. And then finally, between the output of that rectifier and the battery, we'll have a battery current controller that can operate in both regulated current and regulated voltage mode to charge the battery. This is typically then on motherboard with the mobile receivers. So here for a cell phone, showing just highlighted in orange here is all the space dedicated to power management. Again, heavily spatially constrained, needs to be very small. Also limited ability for thermal dissipation, so it needs to be efficient enough to prevent overheating. So going through and looking at average numbers for each of these conversion stages from commercially available devices, see that end-to-end efficiency approximately 65%, and that tends to be relatively on the high end for most commercial demonstrations. We're looking to push towards 90% efficiency, so we're going to have significant improvements across the board in the overall system design and then at each individual stage. So kind of the direction that we're taking is to look at this overall topology and see where we can reduce unnecessary cascaded conversion stages. And looking at this baseline topology, probably the first thing you notice is that I have two back-to-back DC to DC converters in between a rectifier and an inverter. From a high-level standpoint, that's very redundant. I'm taking efficiency hits from both of them. So I can potentially just eliminate both of these and run straight from a PFC rectifier to my WPT inverter. The change that that's going to require is that I can operate this 6.78 megahertz inverter from a high voltage bus if I keep a boost type rectifier. And it's going to require high voltage, very fast switching, low loss power devices. But if I can do that, I can reduce both of these conversion stages. And then I can do a similar thing on the output where I have a couple of cascaded DC to DC conversion stages. I can get rid of one either by widening the range of the integrated battery charger or more likely by changing the rectifier to do some regulation itself using synchronous devices rather than a diode rectifier. So if I implement all of those changes, I can get down to a system that looks like this, and if I couple that with improvements in the performance of each stage, I can potentially get to something like 85% efficiency from AC line to battery, or 90% efficiency from AC line to the connection to the motherboard of the receiver. And then kind of in the limit, if I want to continue down this pathway, I can look at actually going towards a single conversion stage on both the transmitter and receiver, which would combine the operation of a PFC rectifier and an inverter on the primary, and then of the rectifier and the battery charger on the secondary, which would push me towards kind of the theoretical minimum in terms of these topology diagrams where I have a single stage transmitter that goes from 60 hertz to 6.78 megahertz on the primary, and then a regulating rectifier on the secondary, which can do the AC to DC conversion as well as any step up, step down necessary to regulate current and voltage into the battery. And these are things we're working towards. If we can design each of these stages highly efficiently, I may be able to approach 90% end-to-end efficiency. From here, I'd like to just look at each of these individual stages and see how we might implement them and kind of highlight some of the research that we've been doing on each. Starting with just the transmitter itself, just the 6.78 megahertz inverter, if I want to be able to reduce these DC to DCs, eliminate them in between the PFC rectifier and the transmitter, I'm going to need to be able to operate an inverter at some high voltage. If I have here from the AC input my PFC rectifier to some high voltage bus, if it's a boost type PFC, I need this to be somewhere above 170, say the 200 volt range. And then some 6.78 megahertz inverter that I'm just showing here is a half bridge type inverter. On the PFC, since that's decoupled from the inverter through this DC bus, I can design that at whatever frequency I want and design using traditional approaches, and I should be able to achieve 98 or higher. The demonstrations of similar are out there in the literature. So I'm pretty confident that the PFC rectifier can be highly efficient. But there's a question on this 6.78 megahertz inverter operating at 200 volts plus. So I want to look at potential design of that. So down here I'm showing waveforms for this half-bridge inverter if it's operated at full duty cycle and with a load REQ, which models everything else, the transmitter and receiver coils and power electronics. And I'll just assume that those are designed such that the resistance REQ at full load results in the right amount of current. So I don't have to do any sort of duty cycle modulation. I can just operate at 50% duty cycle on the half bridge. Problem with this, particularly switching at 6.78 megahertz, is now I have zero current right at the switching transitions, which means I won't be able to achieve zero voltage switching of these MOSFETs. I could phase delay this a little bit and introduce some reactive impedance, or alternately, if I want to keep everything in phase, I can introduce some ZVS tank here, just a resonant inductor LZVS, which injects current into the switch node of this half bridge in order to allow me to achieve nice ZVS type transitions on the switch node voltage and have reduced switching losses of these two FETs. So if I take an example case of this type of operation and start considering whether or not I can find transistors that will be able to achieve my goals. My goals largely are to be able to achieve 98% plus efficiency out of this inverter. And so I looked at available commercial devices and said, based on the data that's easily available, I'm just going to look at the gate driver losses, this QG times VGS times FS type loss, and then the conduction loss when I'm conducting the resonant current plus some small ZVS triangular current. And This plot shows for an example design with 100 watts output and a 200 volt DC bus, what these two loss mechanisms will be for various silicon devices and GaN devices, all rated at above 300 volts so that they can withstand this 200 volt bus with a little bit of margin. So if I want 98% efficiency at 100 watts, 2 watts will be my absolute limit for losses, and that's this red line. But if I want to consider that my inductors may have a little bit of resistance and I may have a little bit of additional drain-related switching loss, gate driver loss really shouldn't be my dominant switching loss mechanism, maybe I set a more realistic limit down here at 1 watt, which is the yellow line. Now, looking at the segregation here, I can see that this design is fundamentally impossible with any 300 volt silicon devices, and I can well exceed this 1 watt kind of soft limit with a lot of the available GaN devices. So this application is really made possible by the market introduction of gallium nitride semiconductors. I can kind of go a little bit further and say, what if I consider low voltage devices in a multi-level configuration, and it largely doesn't change the conclusion. Some of the silicon devices in a multi-level configuration can start to get close to this 1 watt limit, but still not at all competitive with GaN devices. This is a simple model, and I could do things like implement a resonant gate drive or try to under voltage the drive of the silicon devices, but those are going to require considerable design effort and have significant trade-offs in terms of operation and impact on switching losses related to the drain of the device. So really, what I'm proposing as far as this topology simplification is really made possible by having gallium nitride devices. So to prove that it is possible, I'll show some prototypes that we've built. So the first one is a 2-stage transmitter similar to what I was just analyzing, except in this case it is a full bridge inverter rather than a half bridge. We had a totem pole rectifier using transform devices that was 98.6% efficient at 100 watts, and then a full bridge inverter with ZVS tanks on each leg of the full bridge that we think was about 97% efficient. It's very difficult to accurately measure the output power of this inverter at 6.78 megahertz. So what I can say conclusively is that after some filtering, it was 93% efficient. That filtering was multi-stage inductors, and that had significant loss in it. But overall, we were able to do a 2-stage implementation that, including any filtering at the output, resulted in over 90% efficiency at 100 watts, going from 60 hertz to 6.78 megahertz. More details are available in the reference at the bottom here. From there, we wanted to look at this theoretical limit, which would be a single-stage 60 hertz to 6.78 megahertz topology. And the way we approach that is really by combining these two, the totem pole rectifier and the full bridge inverter. And that resulted in a quasi-single-stage topology that looks like this, where I have on the left a DCM-type totem pole rectifier with diodes on one leg and then a couple of active switches on the other that'll be GaN FETs. That is switched at 6.78 megahertz, and then by switching all of these at 6.78 and operating in DCM so that I can keep a constant switching frequency, I can then use that as the first phase leg of a full bridge inverter. By controlling the duty cycle and phase shift of the second phase leg relative to the first phase leg, I can generate an output 6.78 megahertz waveform from this inverter, with the single phase leg shared with the totem pole rectifier. And again, we had 2 ZVS tanks coupled to each of these two 6.78 megahertz phase legs to make sure that they were soft switching and have some tolerance to any parasitic capacitive loading that might be reflected back through the coil. Combining together in this way means that this shared phase leg has to accomplish both PFC and inverter tasks. Requires constraining the modulation. So here showing these two parameters, beta and alpha, relate to the phase shift and duty cycle of each phase leg. We have to operate on a defined trajectory in order to make sure that we have power balance and effectively accomplish both the PFC and the inverter operation. Here, just showing the actual implementation of this. In the bottom left, showing using this as a wireless power transmitter for multi-receivers and 3 different receivers. We were able to power those all from a single transmitter and single transmitter coil. Showing the 6.78 megahertz waveforms in the top left, and then the 60 hertz waveforms of this thing in the top right. This, again, was about 90% efficient through the entire transmitter stage, including any filtering. One interesting thing that you might notice is that the coil current generated by this is constant from 50 watts output to 100 watts output. In fact, across the whole range of output power, we keep a constant current flowing through the transmitter coil. I'll talk a little bit about why that is in the coming slides. So when I look at the multi-receiver application as far as coil design, there's a couple of issues specific to multiple spatially independent receivers that need to be addressed. First is that the field generated by this transmitter coil is going to be varying depending on the position, so it'll have kind of a radial distribution, but it'll be higher towards the edge of the coil and then fall off. And then second is that even without cross-coupling, reflected load is going to alter the inverter output. If I have a voltage source inverter and I change the load on it, the current coming out of it is going to change relative to that load. So when designing the system, we look at ways that we can mitigate both of these issues, and we came up with two solutions. One is we're going to change the shape of the transmitter coil, shown in the back here, which is a constant field coil design. That will kind of make up here on the receiver surface, on the top of the desk, the flux density relatively uniform, so that regardless of the position of the receiver coil, it'll have a constant coupled flux. And then second is we use an emittance network at the output of the inverter in order to translate the voltage source inverter into a current source type behavior that'll keep constant current flowing through the coil, so that even as the total amount of load power changes, we'll have constant current flowing through the transmitter coil, therefore keeping a constant field. This slide just shows the design of this emittance network. It's really just an LCL where this LF1 and CF resonate together at the resonant frequency. That results in a current flowing through the coil that is proportional to the inverter output voltage and the impedance of the inductor, but has, to a first order approximation, no relationship with the loading impedance, no relationship with how many receivers are present or what power they have. You can design this by looking at Smith charts, looking at the voltage source type behavior of the inverter at the top, and then developing a filter that gives a 180-degree rotation to make it into current source type behavior with the filter. And then as far as the coil design, we looked at is how to make sure that everywhere on this receiver surface we have a constant flux. And so we used a finite element assisted design method for this coil. So on the left here, this blue surface is a flat surface 2 centimeters vertically above the transmitter coil. And I'm looking on the right at the flux density on this surface for various radial positions. So 0 on this axis, on this horizontal axis would represent right in the center of the coil, up to 300 millimeters away from the center of the coil. On the bottom, I'm showing just a cross-section of the coil turns. And then in this plot, I'm showing the magnitude of the flux density and the magnitude of the flux density in the Z direction, which is what will actually couple into a receiver coil. So just for this basic coil where all of the turns are out here at a maximum radius, what I see is that the flux density is really high right above the coils and then kind of peters down as relatively flat but lower in the center. If I start playing around with the spacing of the different turns in this coil, so here just showing a different coil design with a little bit more spacing on the inner turns, you can see that the flux density starts to change, and by spacing them out in this way, I can make it a little bit more flat across the entire radius here. Doing so, I'm going to decrease the radius of some of the turns, which may decrease the Q by decreasing the inductance. But as long as I'm at a length much less than a wavelength, I can gain that back by additional turns. So this plot just shows kind of some perturbation on the spacing of each of the coils, but then around that we developed an optimization routine that looked at finding the optimal position of each of these turns in order to generate a maximally flat flux distribution. And here shows the result of that. You can see that the blue curve, the magnitude of the flux in the Z direction, is heavily flat all the way out to the edge of the coil, very little variation. We combined just the spacing of the coil here together with using some parallel turns. in order to give us a finer resolution of perturbation there. And when we start paralleling turns, we get these interesting geometries where we have to twist the parallel turns together to ensure that the impedance is matched among them and current is shared equally. That was our transmitter coil. On the receiver coils, we don't have these constraints about needing to normalize the flux. Really, we just want to spiral enough turns to generate high enough voltage that maximally couples flux through it. One thing that we've been using that we designed are these series self-resonant receiver coils, which is a simple geometry where I have a couple of planar spirals with a dielectric between them. And then by connecting to opposite terminals on the top and bottom spiral for the actual coil itself, as I push current through this, it's going to flow once around the spiral and then through the dielectric layer, which will generate a series capacitance, so I can get a series resonant characteristic out of it. Without having to add any additional discrete components. And we've built various geometries on various materials and shown that we can calculate and optimize the geometry of this to achieve high Q for the receiver. So here, going back to this image that I showed earlier of our prototype transmitter and receiver coils in the bottom right, comparing that to FEA simulation, we found that we achieved very high Q, good uniform field, and overall good performance. Given the Qs that we've achieved on the transmitter and receiver coils and with a coupling coefficient of less than 0.1, we can predict from that simplified analysis that we could get as high as a 95% efficiency coil to coil for the current system. Okay. On the rectifier, one thing that we really focus on initially in the design of our rectifier circuits is the EMI generation. And just showing how we approached it and why that's going to be a problem here, starting from an ideal diode rectifier. Waveforms on the left are in the time domain on top and frequency domain on bottom. So if I assume I have some sinusoidal current coming in and some output DC voltage, an ideal diode rectifier will reflect back a square wave waveform on VR. Which is going to have high harmonic content out to the very high frequency. Now, either looking at a more realistic diode implementation where they have some parasitic capacitance, or actually introducing some shunt capacitance here, CD, we'll get is lower harmonic content because rather than instantaneously switching from diodes 1 and 4 on to diodes 2 and 3 on, we'll have some period in the middle where we're charging and discharging this capacitance CD, which will produce slower transitions on the voltage waveform, but introduce some phase shift between the voltage and the current and introduce some reactive loading to our system. I can now get rid of that reactive loading by switching to an active type rectifier with all transistor devices, but in doing so, if I push the phase shift back to 0, I'm again going to be hard switching, and I'm going to have very high frequency harmonics because of the nasty waveforms generated when I hard switch these devices. Then taking it one step further and kind of doing something similar to what we did on the transmitter, I can introduce some sort of resonant inductor here, this L-aux, which will generate again a triangle wave of current, which is at a phase such that it'll assist with ZVS. And by doing that, I can push everything back to being in phase, back to being a purely resistive load, without having hard switching while maintaining soft switching and have kind of low harmonic content, giving me the possibility to operate without filters and operate with lower EMI out of the system. So we've designed prototypes of this. This is 6.78 megahertz GaN-based receivers that we built and tested. If you look at the waveforms in the top right, you see that we intentionally try to make these ZVS transitions long. So we actually add additional parallel capacitance to this full bridge, something you might normally not do in these high-frequency applications. But by adding a lot of extra capacitance, we can control the slew rate of the voltage during these dead times and generate, rather than a sharp square wave edge with high harmonics, some kind of trapezoidal type wave that will have lower harmonic content. Here in the bottom right, just comparing this design to a traditional diode full bridge, you see across a wide frequency range we achieve 10 to 20 dB of attenuation, looking at the spectrum of the voltage generated, which will eventually be applied to the coil and potentially radiate from that point. One problem with going over to a synchronous type implementation is that you need to be able to synchronize. Since the receiver itself is fully isolated from the transmitter, you need to have control that can recover the frequency and phase information of the flux field that you're coupled to, and then align switching actions of your transistors such that you can have, for example, a resistive impedance and such that you can stay in lock with the frequency. So we've worked on that and designed some control systems and still have some ongoing work trying to improve this. This becomes a difficult problem at 6.78 megahertz. Even with a 300 megahertz source clock on a digital controller, it results in only about 40 clocks per switching period, which gives you pretty low resolution for time alignment. So the result is, even with stable synchronization, shown here on the top right, there's a little bit of jitter in the waveforms jumping back and forth by a clock to exactly match the average frequency of the transmitter. But by having the synchronization, then we can do things like, while staying frequency synchronized, regulate the phase. In the bottom right, showing just doing output voltage regulation by regulating the phase of the receiver in order to regulate the power flow. And so for a step change in input in this case, you can see the voltage jump up but then be regulated back to its steady state value, all by just changing the phase of this active full bridge receiver. Kind of an interesting one here for, I mentioned the keyboard and wireless mouse that we'd like to power that are low power loads. So we designed, in this case it's actually not a wide bandgap implementation, this is a traditional silicon implementation. At the low power it makes more sense. But in order to address these low power loads, rather than designing a complete system for them, what we designed is a battery retrofit. So we put the power electronics, controls, a battery, shielding, and coils all inside a cylinder the size and shape of a AA battery, so that we can plug that directly into any potential wireless load, and at low power immediately make it into a wirelessly powered mouse just by inserting this battery in a traditional mouse. Okay. So that's the transmitter, coil, and receivers. The last thing I want to talk about before I conclude is more considerations on the overall system. So we went through the simplified analysis of the coils and showed what the optimal efficiency, optimal loading of a pair of coils is and how to calculate it. But as I mentioned, that is independent of the power electronics implementation and what the efficiency and load conditions of each of those are. So if we want to look at the overall system, we have to recognize that these things are not independent and they are fundamentally coupled. In the past, particularly if the coils weren't designed well, they may be dominantly the limiting efficiency of your system, and then you want to just design towards the maximum efficiency of the coils. But as we improve the performance of them and get them towards higher Q, now the losses in the coils may start to become comparable to the losses in the other power electronic stages, and the optimal of just the coils is not necessarily the optimal of the overall system. So in the publication shown here at the bottom, we started to look at, for a DC to DC conversion wireless power transfer system, what is the overall optimal operation, and found that, well, you have to consider the linking between each of these stages, that any consideration, any design decisions on the rectifier will then constrain the operation, constrain the design of the receiver coil, and then those combined constrain what you can do for the transmitter coil, and then all of that dictates what the waveforms have to be on the inverter for a given power. We can work this coupling in the opposite direction, but overall you have to consider the system interdependencies between each of these stages, and we can't just design the best coils and the best inverter independently. We have to look towards designing the best overall system. So with there, I'm just going to conclude. These future designs of WPT systems really need to be looking towards, particularly for consumer acceptance, spatial freedom and multiple receiver as a primary goal. That these things should be transparent. Once I install my wireless transmitter, anything that gets near it should immediately pick up and begin charging, not have to be locked into a fixed spot. Always everything needs to be high efficiency, high power, or small and low EMI. Achieve all of this, we need to look at comprehensive system design. We can't treat all these stages individually. And all of this is really only possible because of the availability of gallium nitride devices, wide bandgap semiconductors. I showed it would be difficult and require a lot more trade-offs to be able to even approach something feasible in terms of efficiency with silicon devices. I'd like to thank sponsors of this work. Currently, that's PowerAmerica, but some of the slides I present also had sponsorship from Intel and the Semiconductor Research Corporation. As well, I'd like to thank NSF and DOE, and then open it up if there are any questions.
Thanks very much, Daniel. That was a pretty thorough and analytical treatment of this topic, so I really appreciate that.
Thank you.
We do have a little bit of time for questions. Because there's so many people on the line, though, I would ask that you use the chat function in the top toolbar of the WebEx application and type your questions in there, and I'll read them out, and then Daniel will answer them. Daniel, are there other safety considerations other than the frequency of the transmitter coil and the power level? I think you mentioned you're using 6.78 megahertz. Mm-hmm. Are there other safety considerations other than those two variables?
Well, so, there's all of the traditional safety considerations of any power electronics. The unique ones have to do with the field generated. It's not going to be completely shielded in an enclosure like many other power electronics applications. Safety is kind of something that continues to need some development. There are these standards like ICNIRP and IEEE has some recommendations. Those tend to be pretty stringent, and they're also, at the moment, somewhat difficult to evaluate precisely. Things like ICNIRP really want full simulations and relating everything back to SAR. They have some general standards on H field and E field. But note that anything above 100 kilohertz, which is going to incorporate all of these potential designs, needs to conform, in addition to the H field and E field, also needs to conform to these SAR rates, which are then more involved to calculate.
Okay.
High frequency makes it kind of nice because you can operate with a lower flux density. So our transmitter coil that I showed is down right at a little below the ICNIRP limit on flux density from the 2010 standard, which is, I think, 26 microtesla.
Okay.
Kind of implies but doesn't guarantee that things conform.
Okay, that answers my question. Let me jump to some of these other questions that people have submitted. The first one is a multiple question. Do you have any issues with shielding? And do you have eddy currents being induced in places you don't want them, such as the metal case of the MacBook you showed in one of the early figures?
Yeah, so that's a practical topic that I didn't put a lot of stress on here, but it is a concern. At the higher frequency, you can tolerate that a little bit more because of the smaller fields, but you do need to design things in a certain way, and if I just threw that MacBook on there with the metal casing and powered up the coil, it would be at best destructive to the operation of the system, and at worst cause some overheating and potentially damage that MacBook. Some papers on ways to accommodate this. A simple one that was designed by Intel is to any hole in that case that you put to install your receiver so that the flux can go through it, just put a slot through the metal of the case on the bottom. What that does is it allows small amounts of eddy currents but reroutes them in a way that they actually increase coupling. So you can get away with kind of low-ish losses, but also higher efficiency of the power transfer by using those eddy currents actually to your advantage to generate higher coupling, almost as a repeater.
Okay, that sounds like a simple solution. The next question is, how fast is zero crossing detection? Any delay will affect the system adversely. Can you please comment?
Yeah, so the synchronization topic is one that's still ongoing. Like I said, we have this solution that we showed could work down to a relatively low power, but still needed high enough current to be able to get accurate zero current detection. Any delay there, if not addressed, will certainly adversely affect operation, but you can address it in a number of ways. If it's well enough characterized, you can just directly compensate that out. particularly if it's stable across operating conditions. You can just say, rather than putting things in phase, put them a couple degrees ahead of whatever my zero current detection tells me. The other way is you can put slower algorithmic type control around this thing, where you say don't necessarily synchronize directly to my zero current detection signal, but use that as a reference and then control the phase between my switching and that signal based on low frequency sensing at the output.
Okay, thanks. The next question is, does the controller design require any current voltage sensors in the receiver side? If it does, which controller equipment is provided, such as high frequency detection?
So it kind of depends on what you want to do with the receiver. So this relates in some sense to the previous question of, if you want to have this active receiver and synchronize well, you need some way of sensing some kind of reference to synchronize to. And we've looked at that using zero current detection, as I showed in one slide. We've also looked at it using an additional coil, single turn or small number of turn coil with no current going through it to sense the flux field. But on the receiver, you need some way, some source that you can synchronize to. And it's difficult because you don't have a pure stiff source. Everything that you can sense there has some sort of relation to when you switch, some sort of relation to the power level that can distort that signal and cause instabilities that you might not think about. And then beyond that, on the receiver, if you have synchronization, depending on what you're doing, but if you want to regulate the output, you need some sort of low frequency sensors at your output, but those are pretty standard. We haven't actually done it on the receiver because of the design and these slow ZVS edges, but could be needed. And what we have done on the transmitter is do some ZVS detection, just coupling in the high frequency elements of the switch node in order to determine whether or not you've gotten some parasitic loading condition that's caused you to lose ZVS and be able to shut down. That becomes more of a protection than a control type of thing, though.
Okay, thank you. Are there any more questions? If you have a question, please use the chat function at the top of the WebEx application or toolbar and just type in your question real quickly. Okay, going once, going twice. Okay, well, again, I'd like to thank you, Daniel, for an excellent presentation that was very comprehensive and well prepared, obviously, and thank you all for joining us today, and please come back a month from in April 3rd for our next technical webinar.
Thanks, Riley, and thanks, everybody, for your attention.
You're welcome. Okay, goodbye. Have a great day.